Hello everyone. In today's video, we are going to discuss about one more shortest path algorithm by name single source shortest path in DAG. Here DAG stands for directed acyclic graph. Now in this algorithm, the first thing that we are supposed to do is for the given input, here the input is a weighted graph. In this weighted graph, first thing that we are supposed to perform is we need to find the topological ordering of all the vertices. Hope all of us know what do you mean by topological ordering. In case if you don't know what do you mean by topological ordering, let me define topological ordering in a simple way. If there is an edge from x to y, in the topological ordering, x should be placed before placing y in the order. So that is the meaning of topological ordering. So assume that this is my graph. If this is my graph, step 1 says that performs topological ordering. I need to perform topological ordering. There are so many ways to perform topological ordering. The most common method to perform topological ordering is the source removal method, or we call it as the vertex deletion method. There is one more method through which we can obtain the topological ordering, that is with the help of the DFS traversal. Let's not worry about how to perform the topological ordering either with the help of DFS method or the source removal method, assuming that we know some method through which we can perform the topological ordering. But please note that what is the definition of topological ordering? I repeat once again, if there is an edge from A to B, if there is an edge from vertex A to B, then in the topological ordering, A should be placed before placing B. So this is the first step. First step is perform topological ordering. So what is the topological ordering for this particular graph? For this graph, the topological ordering is R, S, T, X, Y, Z. Because if you see, there is an edge from T to Y. There is an edge from T to if you take any edge, that property should hold good. That is, if there is an edge is there from T to Y, so before placing Y, T should be placed. So T is placed. There is an edge from T to Z, so before placing Z, T should be placed. So T is placed. There is an edge from T to X, so before placing X, T should be placed. There is an edge from X to Z, before placing Z, X should be placed. Similarly, there is an edge from S to X, so before placing X, S should be placed. Similarly, there is an edge from R to S, R is placed before placing S. Similarly, there is an edge from R to T, so before placing T, R is placed. So I have checked with all the edges, so I have got the topological ordering. Now what is my second step that we are supposed to do? Step 2 is initialize single source. Now for this, let me assume that source vertex, for this particular problem, let me assume that source vertex is vertex R. I'll take it as my first vertex. R is my source vertex. So step 2 is I need to initialize single source. I need to initialize single source algorithm with respect to R as my source vertex. With respect to R as my source vertex. We have discussed this initialize single source vertex while discussing the Bellman-Fold algorithm. That means apart from the source vertex, all other vertex should be marked with infinity and the source vertex should be marked with 0. Now step 3 says, what is step 3? Let me write in simple way like step 1, step 2 and step 3, and maybe at the end of this particular video we will write the entire pseudo code as given in Corman. Step 3 is take each vertex from topological ordering and perform relaxation. Even we have defined, we know what you mean by relaxation. This definition of relaxation and how to perform relaxation we have discussed in the Bellman-Fold algorithm. If you are not sure what do you mean by relaxation, please go back to my previous video and check what do you mean by relaxation. So these are the steps that we are supposed to do in case of the single source shortest path in directed acyclic graph. Note that there are three steps. First is perform the topological ordering. Second one is initialize single source with respect to your source vertex. Here I have taken source vertex as R. Next, take each vertex from the topological ordering. Take each vertex from topological ordering in order. That is, you should take first vertex as R. Then you need to do relaxation. Then you need to take S. You need to do relaxation and so on. Now let's trace how exactly this algorithm works. So how many vertex are there? There are 6 vertex: R, S, T, X, Y, and Z. So perform topological ordering. I have performed the topological ordering. Next is initialize single source. Initialize single source. Let me have even my row numbers denoted with the vertices. Now initialize single source algorithm with respect to R. So for R, I will initialize 0, and for all other remaining vertices, I will initialize infinity. Now this is done. Now what I need to do? Take each vertex from topological ordering in order and perform relaxation. So which is the first vertex in topological ordering? First vertex in topological ordering is R. Now from R, I need to do relaxation. R. So anyway, shortest distance from source to source is 0. Is already 0. So this will obviously it will be 0. This will be 0. So even this entire column, the first column will be 0. Now there is an edge from R to S and there is an edge from R to T. Only this two distance R to S will be updated to 5. That is the minimum value between 5 and infinity is 5. Similarly, the minimum value between 3 and infinity is 3. So apart from these two, all other vertices remains unreachable. In the sense, it remains infinite only. Now I will go with respect to S. S with respect to R. Anyway, I know the shortest distance to R in the previous iteration itself was 0. Now this will be 0 only. Now from S to S. That is, in the previous iteration it was 5. Now also in this iteration it will be 5 only. Because to reach 5, now 5 is having, the S is having 5. So it will be 5. Now from S to T. So S is 5, and from 5 to T is 5 plus 2, 7. 7 and 3. Which is lesser? 3 is lesser. So retain 3 as it is. Now from S, there is an edge to X. So till S, it is 5. 5 plus 6. 5 plus 6 is 11. So this becomes 11. There is an edge from S to T and there is an edge from S to X. Only two values get updated, T and X. All other value will remain as it is. So this remains infinite. Now with respect to T. So this will be 0. I will write this as 0. Because my source vertex is R. So T to S. Now from T, what is the shortest distance to T? T to S. Shortest distance to T is 3. This was a 3. From R, is there any edge going to S? There is no edge. So this will be as it is 5, and even T will be as it is. Now only edges from T to X. And from T to X and T to Z. T to X is 7. So what is the shortest distance to T? It was 3. 3 plus 7 is 10. Next, 3 plus 4. 3 plus 4 is 7. Next, 3 plus 2 is 5. This is about the third iteration. In the fourth iteration, the next element in the order is X. I have taken all the vertices in the order itself. Now X to S. Is there any edge from X to X? No. So this will be as it is. Is there any edge from x to t? No, it will be the previous iteration itself. Is there an edge from x to maybe x to x? Same, it will be 10. X to y, there is an edge x to y with the value of -1. With the value of -1. Now, the shortest distance to reach 10 itself is 10. The shortest distance to reach x is 10. With 10 minus 1 is 10 minus 1 is 9. Now, this is 9. Compare 9 and 7, which is lesser? 7 is less. Retain 7 as it is. Is there an edge from x to x? Yes, there is an edge. X was 10. 10 plus 1, 11. 11 and 5, retain 5 as it is. Next, with respect to y. Is there any edge? I think only edge from y is to z. All other things, I need to only check with this. All other things will be the value of the previous iteration. Now, what is the shortest distance to y? Shortest distance to y is 7. Now, 7 and -2. 7 minus 2 is 5. In the previous iteration also it was 5. So 5, minimum is 5 only. Now with respect to z, just check whether there are any outgoing edges from z. No, there are no outgoing edges from z. So this last row will be as it is. Now we got the shortest distance from R. So what is the shortest distance? That is just right here. R, S, T, X, Y, Z. R to R is 0. R to S is 5. This is the edge. Next, R to T is 3. R to T is 3. Next, R to X is 10. R to X is 10. How you got that 10? R to T this edge and T to X 10. Next, R to Y is 7. R to Y is 7. That is 3 and this particular edge. 3 and 4. Next, R to X, Z is 5. R to Z is 5. How it is 5? 3 and then this 2. This is about how exactly the single source shortest path in a directed acyclic graph works. Please note that first and foremost thing that you are supposed to do is you need to find the topological ordering. Once you find the topological ordering, you should perform the initialize the single source pseudocode. In the sense, you should initialize 0 to source and all other vertices should be marked as infinite. Next, take each vertex in the topological ordering and you need to do a relaxation. We know how to do relaxation. If d of v is the final distance, if d of v is greater than d of u plus cost of u to v, then d of v should be updated as d of u plus cost of c to v. Hope this is clear. We'll quickly see the algorithm and we'll see the time complexity of the algorithm. This is the algorithm. Algorithm name DAG shortest path, which stands for directed acyclic graph shortest path. And this particular algorithm has the 3 input. First input is the graph G, and the second input is how the graph is represented. Now the graph is represented with the help of the weight matrix. So that is my second input, W, and S is the source vertex. So note that this algorithm has 3 input. One input is the graph, the representation of graph in the form of an 2-dimensional array, and the S is the source vertex. So first step is topologically sort the vertices of G. Hope okay with the example that we have discussed, you are sure about what we are supposed to do in this algorithm. So first step was topologically sort all the vertices of the graph. Next is initialize the single source. If you have gone through Bellman-Ford algorithm in my previous video, you must be aware that the initialize single source algorithm has 2 input. One input is graph and the second input is the source vertex. Here the source vertex is S. So the second argument here to this initialize single source algorithm is S. Now third step, for each vertex u taken in the topological ordering, you have to take each vertex in the topological ordering, and you need to do a relaxation with respect to all those vertices which are adjacent to u. In the sense, you need to do a relaxation with respect to all the outgoing edges from u. So this is about the algorithm. Now coming to the time complexity, so how much amount of time the first step says takes in order to perform the topological ordering? If the graph is represented in the form of a matrix, then it takes v square time. If the graph is represented in the form of the adjacency least, then it takes order of v plus e. So this step takes order of v plus e. First step. Now second step, initialize single source shortest path algorithm. So what we do in case of initialize single source, apart from the source vertex, we mark all other vertices as infinity and we mark the source vertex as 0. How much time it takes? It depends upon how many vertices are there. So the time complexity is order of v. It depends upon the number of vertices. Now coming to the third step, fourth step and fifth step. There is a for loop here. So there is an outer for loop for each vertex u taken in the topological ordering. For each vertex v which is adjacent to u, you need to do relaxation. Generally what happens is for all the vertex in the topological order, if there is an outgoing edge, in the worst case, we do v square operation. That means the time complexity is v into v minus 1 by 2, which is nothing but v square. But if you take the aggregate analysis, the meaning of aggregate analysis in the sense, one relaxation, assume that in the entire process, we may do relaxation 10 times. Out of those 10 times relaxation, one of the relaxation may take much amount of time, but all the other relaxation will take a constant time. So that is the meaning of aggregate analysis. Aggregate in the sense it is nothing but the amortized analysis of an algorithm. It is one of the method to understand the amortized analysis. Here the third step, fourth step and fifth step, even though it looks like the relaxation takes more time, only one relaxation in the entire procedure takes more time. But the average of all those relaxation will take a constant time. So let the constant time be denoted with order of 1 or theta of 1. This is by aggregate analysis. I am repeating. Note that it is not v square. On aggregate analysis or by amortized analysis, I may say that, or we can conclude that it takes a constant time. Now, what is the time complexity of this? It is the first part takes order of v plus e time, and the second part takes order of v time, and third part takes the constant time. Among this, asymptotically, which is bigger is order of v plus e. Hence, the time complexity of this algorithm is order of v plus e. Please note that this aggregate analysis, what I termed it as the amortized analysis of an algorithm, we are going to learn in the coming videos. Hope, okay, this is clear? Single source shortest path in case of a directed acyclic graph. Thank you.